Tom, would you like to add?
Well, I mean, space weather, we think of it as like a really large solar flare creates a CME that arrives at Earth and causes a lot of disruption. But that's a space storm. Space weather is how all the changes from one day to the next that occur in the ionosphere. And as we discussed, we thought that would be sort of not that exciting. But near the equator, around the equator where the plasma is densest, that changes drastically from one day to the next, which implies that there's changes in the winds from one day to the next, the background wind that is pushing the plasma this way or that way. And that's not built into any of our capabilities or models for prediction right now. So if we actually see the wind blowing east one day and west the other, that will be a surprising result in and of itself. And we're measuring the effects of those winds immediately. So, there are sun to mud models that are trying to capture this capability of capturing really, if there's something going on in the Midwest, some large storm front that generates something higher, but those have really never been verified. So we're going to be looking at those kinds of things to understand the day-to-day changes in the ionosphere that we can't predict right now.
I just want to do a quick go back to Marsha's question, because I did forget to say one thing, which is I did actually want to do a shout out to the whole team who actually used the most recent couple of months to do a complete test of the observatory to make sure everything was still working. I know sometimes when you think 2 years, you think it's just sat there. No, they exercised they put out the solar panels, they exercised all of the motors. And so it was a really, really beautiful partnership between Northrop Grumman and Berkeley and all of that team that really stood up. And thank you to LSP for letting us do it also. So just wanted to do that.
Sure, and I would just add to that during that hiatus period, the spacecraft was kept under a constant dry nitrogen purge, kept it not only clean but also extremely dry, so that we didn't have any issues with moisture incursion or any other things that might affect the overall electronics capability. And to Nikki's point, we did a full, what's called a comprehensive performance test, a CPT, to exercise all the main elements of the spacecraft, all the software. And then one of the key concerns with the extended period of storage was the potential for a solar array hiccup, if you will, during deployment. We deployed the solar array and it went extremely well, no issues, everything's nominal, and we have a very, very high level of confidence for tomorrow.
Ken.
Ken Kramer, Rocket STEM and Space Up Close. Actually, one of my questions was exactly this, about what you've done to make sure the spacecraft is still operating well. So did you find anything that you had to replace?
No, everything was nominal. I mean, there was a couple minor hiccups, some learning, if you will, but nothing that was out of family. And again, my main concern personally was the solar array with the 5-panel deployment and the extended 9-minute and 10-second deployment sequence. Any minor perturbation would certainly be, I'll say, catastrophic, but no issues, and everything was nominal.
Okay, great. And the science question I have, you mentioned the ISS is in the ionosphere. Is it making any measurements right now? And you might have mentioned an instrument's going up there soon. Can you talk a little bit more detail about that?
Yeah, so there's an instrument that'll launch, I think, 2023, but yeah, thank you. And it's actually, it's picked from our Explorer line. It's a mission of opportunity. It's going up on the ISS, and it is a gravity wave measurement. So it's going to be, again, looking down, doing these big sort of sweeps through the different layers of the ionosphere. And so, yet another really important measurement for us to add to our IT science. But today is all about ICON.
Right, but there's no ionospheric measurements on the ISS made today. Is that right?
That is correct. We don't have any particular ones. We do have CubeSats, of course, that are measuring the ionosphere and the IT system, but from the ISS, other than all of the cameras, you saw all those beautiful images, they're all taken from the ISS.
All right, thank you.
This gentleman here. And then we'll have one question from the phones after that.
Jim Siegel, I'm with Spaceflight Insider. A question for Nikki, I believe. The altitude of this ICON satellite is going to be about 360 miles or so, I understand. So could you provide to my viewers a little bit about the context of that altitude compared to, for example, the different zones in the ionosphere? What other satellites are up there in that region? Also, with respect to satellites that the ionosphere might interfere with, like all of those up in geosynchronous orbit, or 22,000 miles. So could you give us a sense of those distances from the Earth?
Actually, that was your graphic, if you'd like to.
I could
Go-
try to
to
answer
try
the
that one?
question. So, speaking, this orbit has about a 15-year lifetime at that altitude. Your naturally atmosphere drags and slowly slows you down. So not a lot of satellites under this altitude. ISS is in the vicinity. It's a little lower, right? It's lower than 500 kilometers. But that's there's only a few satellites at lower altitudes.
Boosted. The ISS.
The ISS
Yeah.
is boosted, right? So that's why it's still there. We're not going to boost ICON. This is its shot. So we're going to go for 575, and we'll stay there for more than a decade. Above that, DMSP satellites, NOAA satellites, those are usually in a polar orbit. Our orbits, we're flying out of Kennedy because we can, and we want this orbit. It's a 27-degree inclination. It's sort of a science orbit. Many other satellites are in polar orbits, sun-synchronous orbits that are at 90 degrees or a little more than 90-degree inclination. Those are usually about 800 kilometers, 800 to 900 kilometers. So, and then geosynchronous is obviously much farther. The GPS satellites that are interfered with, the density of the ionosphere can cause errors in GPS. Those are in tens of thousands of kilometer orbits and circular orbits, and so I think that's MEO, and then geosynchronous. So,
And what about the relevant zones in the ionosphere? Certain levels, how does that compare?
so we're in the topside ionosphere. So the main peak of the ionosphere is the F layer. It's usually about 300 to 400 kilometers or 200, 300 miles. It depends on your latitude. So the equatorial ionosphere is boosted and pumped up by what we know the equatorial winds that drive a dynamo at low latitudes. There's a natural wind dynamo that drives electric fields that pushes plasma and lifts it up at higher altitudes, but still below us. So we're still in the top side of it. So it's a nice smooth function of altitude with a peak around 300 kilometers, a little higher, and we're in the top of it. So we're still connected to that. Then below that's the E region. The E region's another local peak in the ionosphere that's driven by the F peak is that red layer you see, and that's atomic oxygen. As you get lower, you end up with molecular ions, and those molecules are absorbing a different part of the solar spectrum, and you get another peak. And that's where you have this strong interaction. And that's where you wish you could spend your time, but we have to look at it remotely. So the E region is around 120 to 180 kilometers, or above, above, just below 100 miles. And that's a good spot for us. That's the other region of the ionosphere that's really important to ICON.
And geosynchronous is much higher, and they really worry about the radiation belts. So they're in the outer belt of the Van Allen radiation belts, which also respond to space weather, and so often can become extremely, extremely active, lots and lots of high energy particles, and the entire radiation belts can grow and engulf spacecraft that don't really want to be in the radiation belts. And so they worry more about that.
What's the altitude of that?
6.6 Earth radii is the easiest one for the geosynchronous spacecraft. I can think about it in miles.
Think about it.
Yes.
Thank you.
Great. We will go to the phones. We have Chris Gephardt with NASA Spaceflight.
Yes, can you hear me?
Yes.
Okay. Thank you for taking my questions. I've got two. For this particular mission, why an equatorial orbit instead of a polar orbit? What does this orbit advantage give you over a polar one? And for Northrop Grumman, can you go over and sort of outline, since the last launch attempt a year ago, what have you guys been doing with Pegasus, and what were the fixes or the root cause of that issue that you identified and fixed for today or for tomorrow's attempt? Thank you.
So I think Tom's going to answer the why equatorial, and we're going to hold your question on the Pegasus because you're going to have a whole briefing on that launch system. So if we can hold that one to the next panel when the real experts are up here.
Well, there's a graphic for this somewhere else, not here, but it shows how from an equatorial orbit and the way we make our wind measurements, when we are crossing the equator, our wind instrument is making measurements to the north of the satellite. And we end up on that same field line that you're connected to when you're at the magnetic equator. You follow that dipole field line down, you can follow it down to where the wind measurement is made. And that's not achievable with a polar orbit. You have to be in a near equatorial orbit. There's a trade-off as well that the low latitudes are also where some of the largest, let's say, there are tides in the upper atmosphere, which originate in the lower atmosphere. These and they're not gravitational tides. They're not a lunar tide or a solar tide. They're just a motion. They're a motion of the atmosphere that's supported by on the planetary scale. Those are largest at the low latitudes. So we're focused in the low latitudes for a couple of reasons.
That's where all the action is happening. That's why we want to go there.
That's why whereas icons goes where the action is.
Icon goes where the action is.
We have another question from the phones. It's Megan Bartell with space.com. I think.
She's on mute.
We can't hear. I'm going to try one more time, Megan. We will move on. Any last questions from the room before we change it up? We will be going on to our second panel then. We are going to move. In the meantime, we have a video for you showing the launch sequence and deploy. We are back with our new panel. We have now Omar Baez, who is the NASA Launch Director, and Phil Joyce, who is with Northrop Grumman. He is the Vice President of Space Launch Programs. And we are now going to hear a little bit more about what brings us all the way to launch tomorrow. Omar.
Well, thank you. First off, I want to thank the media for being here. This is how we get our message out primarily to our taxpayers who are funding this. So thank you for being here and being that conduit for them. And I do want to thank our team that I have the great privilege of leading, starting with Launch Services Program here at Kennedy Space Center, our partners, Northrop Grumman, our customers' headquarters, NASA headquarters, and NASA Goddard Space Flight Center, and our ultimate customer, which is Thomas, who you heard before at UCB Berkeley. And I want to apologize for delaying you guys for the last 11 months, but we wanted to get things right on this rocket. There was no, we have no second chances on these type of missions, and we want to get it right. In the months that have preceded this, we've done a number of tests, both on the ground, and we've taken the rocket up with the L-1011 several times to try and lick this thing. We're only able to see it in flight, and flight's a very difficult thing to model on the ground because you have several components going on at once. You not only have the altitude, you have the vibration, you have the air buffeting you, the airplane's making its own vibrations with its turbines going. The atmosphere is a little bit less as we go up, and funny things happen when you're at altitude, and the temperatures get colder, and it's we had a system that we had a new component go in there, and quite possibly we may have seen this gremlin show up before, but we didn't have a visual cue into it. Now we did, and we had to do something about it. And that's what's taken us this long to come to grips with what those things were that were making our rudder position indicator get active. Something that we don't want to see in flight, and something that we haven't experienced since we put several fixes in. So I hope that kind of explains what we've been doing. We did put the spacecraft aside while we did these tests so that we didn't put it in harm's way. And if we could roll a video that I have. This is the Icon spacecraft. And this is the solar array deploy and CPT that they spoke of earlier. This was done in August into September to make sure that during the hiatus that the spacecraft was off in a corner being kept in conditions that something didn't go wrong. This is a shot of the spacecraft being mated to the Pegasus. This happened on September 9th. On September 25th, we brought it out to the first reusable zero stage, that L1011 Stargazer that you see there. And this is the flight crew bringing it into the on its ferry flight here on October 1st to the skid strip at the Cape Canaveral Air Force Station, which I want to thank the folks at the 45th Squadron here and the folks at the 30th for supporting us all the way through this. And so I said a lot, and we saw this video. The important thing is tomorrow. The team will get working on the rocket about 2 in the afternoon. We'll have our management on station about 5 in the afternoon. They'll be powering up the Pegasus, the L1011, and hopefully, if all goes well, we'll lift off from the skid strip about 8:32 in the evening, and 58 minutes later, we'll be in the drop box, and we'll be able to drop Icon and the Pegasus and light it up and set it on its way. We do have a 90-minute window, so if the first attempt is aborted or we're late doing something on the ground or the weather gets us, we do have a short buffer there of about an hour, hour and 15, where we can adjust and still make it so that Icon can launch tomorrow. And with that, I'll turn it over to Phil Joyce.
Well, thanks, Omar. I want to second a lot of the things that you said about all the people that have been involved to get us to this point. You know, it's really says something about a team when you have a lot of adversity, and Icon is certainly no different. This is an incredibly complex machine. We saw some things on our previous launch attempt that none of us were comfortable with, and we decided to stand down and go address those and make sure that we really understood exactly what was happening there. That required, as Omar said, a really extensive ground test, modeling, simulation, and flight test activity to get to the bottom of what was really an extremely challenging problem, one of the most challenging that I've seen in my career in this business over some 30 years. But we got there. We with NASA, were able to get to some surprising results that told us a little bit more about the system that we have on the Pegasus, and educated us to the point where we could make some really smart corrective actions. So we implemented those. We got all the stakeholders on board, and I want to thank the science team and the headquarters team and all at Goddard and at Berkeley for sticking with us and actually being part of the solution here. And I think it says something about the strength of our relationship and the teamwork that we've enjoyed at Northrop Grumman over the last 3 decades on Pegasus with NASA. It's been a very special relationship. It's one we will continue with NASA. But all the things that we did in terms of qualifying and the flight tests that we performed with the system in its modified state give us great confidence that we're ready to go. And there's nothing better than a launch day, and we're all fired up and ready to go at Northrop. Looking forward to giving Icon a great ride.
Fantastic. We will go to questions in the room, and then we'll take them from the phone as well. Sir.
Jim Siegel with Spaceflight Insider. I understand that this is the 44th mission for Pegasus. Can you tell me if there are any future missions on the books, and when will the next Pegasus mission be?
Well, we don't have any current contracts, but I'm happy to report that we have two Pegasus vehicles out of Vandenberg that are in a pretty advanced state of integration that are available. We're talking to several potential customers for those. Our L-1011 aircraft is as healthy as ever. The team at Mojave that maintains that airplane keeps it in tip-top shape, as illustrated by getting out here without any major observations or problems on the aircraft. So that aircraft's going to be supported for the foreseeable future, and we're looking to continuing Pegasus for as long as there are customers.
Steve Clark, I think you were.
Hi, Stephen Clark from Spaceflight Now. Could one or both of you sort of talk in a little more detail about what exactly you were seeing on the launch attempt last year with the rudder movement, and what the investigation showed was the cause, and what corrective actions you implemented to resolve it? Just some more detail. I'm not sure I ever really fully grasped what you were seeing.
Yeah, so the Pegasus Stage 1 flight is an airplane, right? So there are three control surfaces on Stage 1, two elevons and a rudder. And it was the rudder actuator that we were seeing some anomalous position feedback readings, basically noise spikes in the feedback line. We didn't understand those, but they were significant enough that we were concerned if we launched with that condition present, that those noise spikes could couple into our control system and cause a bad day. So we elected to stand down at that point and do an investigation. We pulled that hardware off the rocket. We got it into our labs in Chandler, Arizona at Northrop Grumman, and basically replicated as best we could on the ground. And Omar pointed out how difficult this is to do on the ground, the environment that system was seeing while it was being carried around at 40,000 feet and minus 40 F on the L-1011. We were able to do that and set those tests up and able to recreate the problem, and that enabled us to get to the cause of it and identify several parts of the system that made us a little bit more vulnerable to that kind of a noise. And so as any kind of a complex problem like this, and this is why the investigation took a long time, usually has several causal factors, and this one was no different. There were actually 5 or 6 different things that we thought were coupling into this phenomena that we were seeing, and what we did to correct the problem is we went and attacked all of those. And so we modified our electronics to be less sensitive to this. We modified some of the hardware in that feedback circuit to be more robust to the environment that the L-1011 provides, which is a very unique and challenging environment. And then we went back and demonstrated that the modified systems would handle those environments in the lab. And then we conducted 2 test flights out at Vandenberg, one that simulated a sort of a ferry flight, the one we just did last week, the other that simulated a launch attempt where the L-1011 is configured a little bit differently, and we could see a little bit different environments, and verified in both of those conditions that we didn't see any of those spikes return. And then the final test, and all of us were on pins and needles for 5.5 hours while the aircraft transferred from Vandenberg over to the Cape. We were monitoring that circuit the entire flight, and we're very happy to report that it was as clean as anything we've seen. So that gives us great confidence going forward into tomorrow's attempt that we've got this problem behind us. But just in case, we've instituted some new mission rules to look for these kinds of things, and with NASA, we'll evaluate anything we see during the launch attempt and make a call that is completely based on mission success, because that's what we're all about here, is getting this satellite to orbit.
Great. Oh, follow-up?
Just a quick follow-up for Phil. You mentioned the new hardware on this mission. Are those the fin batteries that are flying for the first time? And was there any relationship between that and the signatures you were seeing?
The fin batteries are actually not new. They're the legacy thermal batteries that we've been flying on Pegasus for years, many years. The actuator control unit, the electronics that control the servo on the actuators themselves, that is new, and that is one of the components that we did some slight modifications to correct for this issue.
Marcia.
Marcia Dunn, Associated Press. Where will the drop actually occur? Where will the plane be? At what altitude and how many people on board for the deploy?
So, Marcia, we're going to be about 100 miles, 50 to 100 miles off of Daytona Beach when the drop occurs. We do have a 40-mile long box to be able to launch it in, but you're going to get a special treat, and you're going to hear all about the flight crew and the airplane in the next panel.
And what's the altitude for the drop?
39,000 feet.
39,000. Thanks. Okay.
Great. We do have a question from the phones. Was a question from Chris Gephardt, NASA Space Flight.
Yes. In terms of that Dropbox location, you can launch anywhere within that, if I'm understanding it correctly, right? So if there's a thunderstorm at the preferred drop location, you can reconfigure and get to another part in that box away from weather if needed. Is that correct?
In theory, yeah, that we could steer around it, but the last thing we want to do is fly a airplane with a rocket under it anywhere near a thunderhead. So yeah, if the conditions are right and we're able to get either away from the thunderhead or high above it, we might be able to do something. But in reality, most thunderheads are anywhere from 10,000 feet to 50,000 feet or more. So it would be very unlikely, but we can certainly steer around some of them. And we can delay the flight or loiter for a little bit and do another run in case time is helping us in having that thunderhead or whatever it is we're trying to avoid move off.
Any more questions from the room before we move on? Yes, sir.
Jim Siegel from Spaceflight Insider. Question for Phil. So the Pegasus concept, dropping a rocket from an airplane, is very unique. Is anybody else anywhere else in the world doing that, or is this unique to Northrop Grumman?
Well, you may have heard of our friends at Virgin Orbit. So their concept looks very similar to Pegasus. There's no wing on their rocket, and they launch it from a 747. But we're really proud, and it's part of the Northrop Grumman and prior to Northrop Orbital Sciences legacy. The Pegasus was the first privately developed space launch vehicle and the first air-launched space launch vehicle with the first flight in 1990. And as noted, this is Mission 44. And it's been a very robust system, capable of 1,000 pounds to low Earth orbit, can launch from anywhere in the world, and it's one of our crown jewels.
Thank you. We're going to move on to our third panel. And as an intermission, we're going to show you a movie on the Cygnus launch. This was NASA's last Pegasus launch from December of 2016.
LC, PLT, copy.
LC Peg, Peg is go for launch.
PLT, LC is go for launch. PLT confirm.
LC, PLT, PLT confirms go for launch.
Drop on my mark. 3, 2,
1. Go for release.
Pegasus is away.
And drop. Pegasus is away.
LC, PLT.
Ignition of the Pegasus rocket with Cygnus, helping hurricane forecasters understand and predict the intensity of hurricanes.
Hello, we are back. We now have with us Bill Ulrich from the 45th Space Wing. He's a weather officer. We also have Don Walters, who is the chief pilot of that Northrop Grumman Stargazer L-1011 that we were just hearing about. And we're going to hear a little bit more about what we can expect tomorrow night. So for starters, Bill, tell me, Will, I'm sorry, apologies. tell me a little bit about why the 45th Space Wing and weather's important here. What are you bringing to the
Yeah, the 45th
launch?
Space Wing and the 45th Weather Squadron, our primary mission is to ensure safe access to space, and of which the 45th Weather Squadron, of course, is the weather component. So to ensure that our launch customers in the Eastern Range are launching into safe weather conditions, we use a variety of weather tools to ensure that they are doing so, including weather radar, high-resolution satellite imagery, lightning detection equipment, as well as weather balloons. And we use all of that equipment to evaluate a total of 10 lightning launch commit criteria, or 10 rules basically that we need to ensure that the customer is not launching into adverse weather conditions. And those 10 rules are really meant to steer the vehicle clear of any potential thunderstorms that are ongoing or could potentially develop, or those clouds that could potentially trigger lightning with the presence of a rocket in the vicinity. So this particular mission is a little bit challenging in the sense that we're talking about the drop box being about 50 to 100 miles offshore. So it's not really in the presence of some of these ground sensors that we typically use when we launch from anything here at Cape Canaveral. We're talking about something that's 50 to 100 miles offshore, but we can still supplement that information with our radar here at Patrick Air Force Base, as well as high-resolution satellite imagery. So ultimately, at the end of the day, we'll still be able to evaluate most of those lightning launch commit criteria to ensure that they launch safely. It also helps that they're also going to be launching from 39,000 feet in the atmosphere above most of the weather that we experience here on the ground.
And so what's the answer? What's the weather going to be like?
Oh, geez. I knew you guys were going to ask me that question. Unfortunately, here I am on the stage again being the bearer of bad news. I feel like I have been for the past couple of launches, but the good news is the launches have eventually gotten off the ground, and eventually this one will as well. But for tomorrow, if we take a look at satellite imagery right now, we've got a couple systems that are going to kind of interfere with tomorrow's launch. And you can see all that organized cloudiness off the east coast of Florida, stretching up the eastern seaboard. It's all associated with a large area, a surface trough, basically, which is an immature area of low pressure that is triggering those showers and thunderstorms up and down the east coast. What you can't really see shrouded underneath all of those clouds up and down the eastern seaboard is a cold front. And that cold front is expected to move a little bit closer to us during the day tomorrow, and then it's expected to shift a little bit further to the south on Thursday. So if we look at tomorrow's forecast, with the presence of that surface trough and that cold front to our north, conditions will be quite unstable tomorrow, kind of like they are today, kind of like they were last night, such that we expect scattered showers and isolated thunderstorms in the area, even tomorrow evening. Now, the winds and the temperature that you see there is what the conditions are expected to be for takeoff, which is, light winds out of the northeast, 7 to 9 miles per hour, and temperatures in the low 80s. But there will be, unfortunately, scattered showers in the vicinity of the area, but also, and especially, there'll be even more activity out over the Atlantic water. So our primary concerns are the cumulus cloud rule and the lightning rule. And with that, unfortunately, we do have a probability of violation of 70%. But if we go to the backup day, hopefully we don't need to have a 24-hour delay, but should we, conditions are going to be a little bit better. For takeoff, we're going to have a slightly stronger winds, unfortunately, which can be a crosswind can be an issue for takeoff. The winds will be out of the northeast around 15 miles per hour. But overall, the coverage of showers is expected to be lower as we see that cold front, or what's left of the cold front, I should say. It's still kind of early for us to have a cold front here in central Florida. What's left of it will start to bring in some drier air from the north. So overall, our primary concern is the cumulus cloud rule with a 40% chance of POB. So I wish I had some better news, but ultimately we're going to do our best with all the tools that we have at our disposal to ensure that tomorrow's launch or potentially Thursday night's launch is as safe as possible. Thanks.
Thank you very much. Let us go to Don. Tell us a little bit about piloting, hopefully with good weather, what that experience is like when you take off.
Well, thank you for the weather briefing. We rely on a large group of people to give us information to ensure that the safety of the flight, that's our primary concern, is the safety of the flight. On the ground, our main concerns are precipitation, winds, and lightning. Once we're in the air, one of the advantages of the L-1011 system is that it's a very mobile, very fluid system, and tactically we can move around some of the storms that we're talking about. Once we're in the drop box, of course we have to have a clear shot for the rocket, But the crew has some flexibility to help deviate around some of the storms locally. But on the ground for takeoff, it's just water, wind, and lightning.
So I think we have a video of the path that you expect to take. Can you talk us a little bit through the entire process of dropping off?
Absolutely. So we've planned a 58-minute flight. The goal is for us to be at the launch box at a specific time, at a specific speed, at a specific altitude. So we'll be taking off out of the skid strip, flying a pattern away from the launch box to gain altitude. As soon as we gain altitude, we're going to turn back towards our launch point and take weather observations over the launch box so that we know the wind, the temperature, the turbulence, and the cloud conditions. Then we'll fly out around, turn around, give us time to configure the systems for launch. When we hit the launch box or hit the launch point, we'll drop the rocket, turn slightly out of the way, and watch the rocket fly off into the west.
So I have a question for you because you've talked to me about this before. What it feels like when you're in that plane and you drop the Pegasus.
So it is the most exciting part of the flight. You can imagine we take a 52,000. The plane is flying in a stable condition. When you drop 52,000 pounds all at once, the lift that was on the airplane still exists, and as the rocket falls, we lose that gravity. We lose the 52,000 pounds. So the plane climbs fairly rapidly, about 1,500 feet as the rocket is falling. Not only is that an exciting part of the flight, but it also gives us separation for safety from the rocket as we drop it.
All right. Well, we are hoping for smooth skies tomorrow, and we will go to questions in the room. Marcia.
Yes, Marcia Dunn, Associated Press. How many people on board for the launch, and how many seconds after the rocket drops does it ignite, and who's actually somebody pushing a button, or is it all automated at that point following the drop? How does that?
So the number of people on board, our minimum crew for a launch is 5. We have 3 pilots and 2 launch panel operators. Occasionally, we do bring additional pilots or launch panel operators along for training. I think that we'll have 7 on this particular launch. The rocket drops for 5 seconds before ignition takes place, as long as all of the safety parameters in the rocket are go for ignition. And what was the last question, Bart?
Does someone on board provide?
So the unique part of Pegasus is that when we fly into the launch box, the crew is just sort of the instrument for a huge team that's on the ground monitoring all the safety parameters. So as soon as we are in the launch box, we wait for a command from our launch conductor to drop the rocket, and it is actually, he's sitting right behind you, my co-pilot, Steve Gunn, is the one who actually flips up the switch and physically drops the rocket.
And the ignition, is that also done from the crew
No,
on
no.
board?
Once the rocket is clear of the airplane, it's completely autonomous.
Autonomous, okay. Thank you.
Steve Clark.
Hi, 2 questions for Don. Since you've done this before, can you describe the sort of the physical sensation of that feeling on the airplane when it wants to climb so quickly once you let go of that 52,000 pound rocket? And I have one follow-up.
Sure. Well, the best way I can describe it is if you've ever ridden in a ride that pushes you down in your seat rather quickly. So as we lose the weight, the airplane rises at a fairly rapid rate, and you can feel, there's 2 things that you feel. One is that you can feel yourself being pushed up against the seat. The second thing that happens is when airplanes fly, we balance them. We have a term called weight and balance. And so when we drop the rocket, it changes the balance of the aircraft rather dramatically, which creates this pitch-up moment. So what winds up happening is we let the airplane climb to not resist that too much, exceed a structural limit. And as it starts climbing and dissipating energy, then we can push over and kind of level the plane off again.
And just to confirm the numbers, what's the target altitude, airspeed, and azimuth for the release, if you have that?
The target altitude is 39,000 feet. Our target airspeed for launch is about 0.82 Mach, and our launch heading is about 113 degrees magnetic.
All right.
Jim Siegel from Spaceflight Insider. Two questions. First of all, is there a certain meeting that takes place tomorrow at a certain time at which it was going to be decided whether the weather is going to be favorable or not, or is it kind of all the way up till launch time, or time where you take off around, what, 8:30 or something like that? And then the second question is, what happens if both Wednesday and Thursday are not acceptable from a weather performance? Then what happens? Is there a backup date after that, or what?
And we're wrapping up, so answer quickly.
Okay, so yes, there will be a meeting tomorrow. Our senior management meets with NASA to decide what the risk factors are and what the probability of success is. And I believe we have Thursday and Friday as backup days.
Fantastic. Thank you all so much today. We had one quick question we weren't able to answer, and I want to make sure that Nikki is available to answer that question now, which was the cost that was asked earlier.
Okay, so the cost, the NASA cost for ICON is $252 million, and we're happy that we have not violated that cost at all. And for those of you who don't do Earth radii, geostationary is 22,000 miles up from the above the sea surface.
Fantastic. Please tune in for the the launch coverage, which will be tomorrow night, nasa.gov/live. And for more questions about ICON, nasa.gov/ICON. We've had great fun today. Looking forward to tomorrow. Bye.
Hey, you're watching NASA TV, on the air and online every day, on this planet and beyond.
Station, this is Houston. Are you ready for the event?
Houston, this is the station. I am ready for the event.
ESA, this is Mission Control Houston. Please call station for a voice check. ESA, this is Mission Control Houston. Please call station for a voice check.